So in 3.4, we're going to discuss perpendicular lines. And we talked about perpendicular lines before, so we're going to talk about perpendicular bisectors to start off with. And when we discuss perpendicular bisectors, a perpendicular bisector of a segment is actually just a line that is perpendicular to a segment at the segment's midpoint. So if I were to draw out a segment, I'm going to draw it out here up top. I got a little bit more room. So here's my segment. And if I wanted to draw in a perpendicular bisector, that would be a line that would be perpendicular to the one that I've drawn, the segment that I've drawn, at the midpoint. So if I were to figure out where the midpoint of the segment is, and then draw in a line that would be perpendicular, we would say that this line right here is a perpendicular bisector of my segment, because not only is it perpendicular to the segment, but it also bisects that segment because these two are congruent. That's a perpendicular bisector. Now, this kind of leads us to a fun little fact that if we're dealing with perpendicular bisectors, the shortest segment from a point to a line is actually going to be perpendicular to the line. And this fact is actually used to define the distance from a point to a line as the length of the perpendicular segment from the point to the line. So what does that all mean? If I have a line, and I have a point, some random point, the shortest distance from this point to this line is going to be produced by the segment that would be perpendicular to the line and goes through that point. So the shortest distance from a point to a line would be the one that is perpendicular to it. And it makes sense because let's talk about it this way. What if I were to try to draw in maybe a line segment over here? This is definitely larger than the one that is perpendicular to line. And so is this one, and so is this one, and so is this one, and so is this one. So the shortest one only occurs when it is perpendicular to my line. So using that fun little fact from the previous slide, what we're going to do is we're going to go ahead and use this diagram off to the side. And we're going to name the shortest segment from point A to the line BC. So here's my point. It's point A. And we want to know what is the shortest segment from point A to the line BC. Now we said the shortest distance from a point to a line is the one that is perpendicular. So if I'm looking at it, is it going to be the line segment AC, the line segment AP, or the line segment AB? Now hopefully common sense plays a little bit of a role here also, and you notice that the line segment AP, which is the perpendicular one, is going to be the shortest from the point A to the line BC. So I would say that AP, that segment, is the shortest segment from point A to line BC. The second part of this example asks us to write and solve an inequality for x. Now I notice that I'm working with x and it's labeled here on AC. It's x minus 8. The only other value they give to me is for AP, and AP is 12. Now I'm looking at this and I notice I really am working with a right triangle here due to that right angle. And in a right triangle, we all know that the hypotenuse is the largest side of a right triangle. So if I set up an inequality, I know I'm using x minus 8, and I know I'm using 12. The biggest thing here, though, is the x minus 8 greater than 12, or is it less than 12? Hopefully you said it was greater than 12 because it's the hypotenuse. So that's my inequality. Now, with this, if I add 8 to both sides, I end up getting x is greater than 20. So that means in order for this to actually be a true diagram and for it to work out, we would have to have x be greater than 20, because anything greater than 20 would give us a value that is greater than 12 when we plugged it in. It cannot equal 20 because if I put a 20 in for the x, 20 minus 8 would give me 12, which means it would equal this leg, and therefore it would not be a hypotenuse.
Okay, we're just going to run you through some theorems here. The first theorem simply says, if two intersecting lines form a linear pair of congruent angles, then the lines are perpendicular. So that means I've got two lines intersecting here. Here's line L and M, and they're crossing each other here. And if you end up with a linear pair of congruent angles, so here is my linear pair of angles, and they're going to be congruent, then that means that they have to be perpendicular, meaning that both of those angles are going to be right angles. The next one says, it's the perpendicular transversal theorem. It says in a plane, if a transversal is perpendicular to one of two parallel lines, then it's got to be perpendicular to the other. That's kind of self-explanatory. If I've got parallel lines here, N and P, and I've got a transversal that cuts through them, well, if it's going to be perpendicular to one, it's got to be perpendicular to the other. Remember, N and P have the same slopes. They're rising and they're running at the same rate, pretty much. So if they have the same slopes and you got a line that cuts through them, if one of them is going to be 90 degrees, the other one's got to be 90 degrees as well. And the last one kind of sort of goes the backwards version of that. It says if you have two coplanar lines that are perpendicular to the same lines, then those lines have to be parallel. So that means if I've got two lines, so here's R and S, and they're perpendicular to the same line, so they're both perpendicular to my transversal, then those two lines have to be parallel, meaning that they rise and they run at the same rate. So therefore, if it's perpendicular for one, be perpendicular for the other, and then those lines have to be parallel. It's everybody's favorite two-column proof, right? We have our reasons and we have our statements. So our statements and our reasons here. Oops. Okay, it tells you that R and S are parallel to each other, and then it also tells you that angle 1 is congruent to angle 2, and they want you to actually come up with R and T being perpendicular here. Okay, so step number 1, actually let me move this over, I don't know why I wrote this so close. Step number 1 is actually going to be R given. So let's say we've got 1, we've got R is parallel to S, and we've got angle 1 is congruent to angle 2. Remember, this is going to be our given. Okay, now let's think about this. If I know that R and S are parallel, and we know about these angles inside, you should know that 2 and 3, they make this F here, are corresponding angles. So 2 and 3 should also be congruent. So step number 2, I'm going to write angle 2 is congruent to angle 3. And the reason why, you guys, well, these are corresponding angles. So this would be the corresponding angles postulate. Okay? So now let's take a look. If 1 is congruent to 2, and then 2 is congruent to 3, well, that would have to make angle 1 congruent to angle 3. I cut out that middleman there, so this is actually going to be my transitive property. Okay, so now let's take a look. Remember, my goal is to show that R and T are perpendicular, and I just told you that 1 and 3 are congruent. Well, let's take a look here. If 1 and 3 are congruent, oops, I don't know what happened to my pen. If 1 and 3 are congruent here, they also fall in the same line. Well, we just learned one of the theorems about this. If these two lines form a linear pair and they're congruent, then they have to be perpendicular. Right? These two lines have to be perpendicular. So, I actually just found out that R is perpendicular to T, and the reason why, well, these two intersecting lines form a linear pair of congruent angles. Okay? This makes the lines perpendicular, remember? This was the very first theorem, 341, that we learned. All right, you guys need to get used to this. You're going to have to get used to writing these proofs out for the problems. Make sure you write down some good questions, and we'll see you tomorrow.